howdy, this is Mr. Potter. In today's lesson, we're going to talk about the derivative function, which is the key to the idea of differential calculus. And we start by taking a look at what we talked about in the previous chapter, which was the instantaneous rate of change at x equals a point. Remember that we were originally talking about just average rate of change, which is our y2 minus y1 over x2 minus x1. And so we talked about this in terms of a function, f of x2 minus f of x1 over x2 minus x1, but we wanted to do it as this difference between x1 and x2 got smaller. So what we would do is we would say the instantaneous rate of change would be equal to a limit as h went to 0 of f of a plus h minus f of a over h. And of course the idea is that if I was to do just a direct substitution of h equals 0, I'd end up with the 0 over 0, which doesn't help me. But I also know that when we talk about 0 over 0, we're talking about a factor that's common in the numerator and denominator. And so what we would do is we would eliminate that factor and then be able to evaluate that limit directly. And we touched on the subject of, well, this value of the instantaneous rate of change really does depend on the value of x. So we talked about the instantaneous rate of change as being a function of x, where I could talk about the instantaneous rate of change at a particular point by evaluating the limit as h approaches 0 of my function at that particular point plus h minus my function at the particular point, all divided by h. And so what happened is we had this instantaneous rate of change as a function of x. And this really is the key idea. This is the idea of the derivative function. The idea is that this function comes from our original function. It's derived from that function. It's almost as if it's an image of this function. And so our notation says that we write our function's name with a prime symbol. So I can talk about f prime of x being the symbol for the derivative function. And this is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And this is one notation that we have. We can also talk about the change of a function with respect to its independent variable x. It's just a different notation, but it represents the exact same idea. The limit as h goes to 0 of my function at x plus h minus my function at x, all divided by h. And the reason we have for this differing notation is because calculus was co-discovered by two mathematicians, Newton in England and Leibniz on the continent of Europe. And Newton was talking about derivatives from his work with fluxions. And so he was talking about how he would have a function and its derivative function. And he would use this dot notation over x. And due to typographical limitations, we started writing this as f with a prime symbol. And so we'll see f prime, we'll also see f prime of x, we'll also see y prime or y prime of x, because we're used to seeing y being a function of x. And so this notation, this prime notation, comes from the work of Newton. Leibniz, on the other hand, was dealing with this derivative as we started off with, from the rates of change, the delta y over delta x. And he considered this idea of taking it so that the distance between two consecutive x coordinates being infinitesimally small to kind of be this next leap forward. And so he likened it to the leap forward from the Greek civilization to the Roman civilization. And so what he did is he transformed this Greek delta to the Latin d. So we would talk about dy over dx. Or he would also talk about df dx. And sometimes he would use the idea of a differential operator because it does transform a function. So we talk about the change with respect to x of a function. So d dx of f or d dx of y. And these are a lot of different ways of saying the exact same thing. What is the function that represents the instantaneous rate of change? What is the function that represents the slope of the tangent line? What is the function that represents the speed when our function of position is given. All of these are applications for the derivative function. And so in our class, we'll be using all of these notations fairly interchangeably. One of the things that's nice with Newton's notation is that it's relatively simple to write, especially if it's just f prime or y prime. Whereas the ideal part of Leibniz's notation is that it's clear what my independent variable is. So I can talk about a change in x, or I can talk about a change in t if I want to talk about the change in height with respect to time. It's real easy for me to clearly state my dependent and independent variable using Leibniz's notation. It's not necessarily as easy with Newton's notation, but I can do that by explicitly listing my independent variable in functional notation. So these are all notations that we'll be using in this class, and all of these represent the same quantity. So I want to talk about this from how do we actually calculate the function that represents the instantaneous rate of change. So what I've got here is I've got a function y equals x cubed. And I know that my derivative function is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So I need to evaluate x plus h cubed minus x cubed over h as the limit as h approaches 0. And so I need to expand this binomial, and that's going to give me the x cubed plus 3x squared h plus 3x h squared plus h cubed. And this is already as simplified as I can get it, x cubed, all divided by h, the limit as h approaches 0. And just as before, I noticed that my original function always seems to make a 0 pair with some terms in this expanded function. And the remaining terms of this polynomial have a common factor of h. So I can factor an h out and be left with 3x squared plus 3xh plus h squared, all divided by h, the limit as h approaches 0. And because I have a common factor in the numerator and denominator, it divides out. And I have a polynomial where I can directly substitute h equals 0 in. And this gives me 3x squared. So in this situation, I would say that my derivative function is 3x squared. And I can use it using either Newton's notation or Leibniz's notation. Either one is perfectly acceptable. And what this means is if I take a look at my cubic function, which does tend to look something like this, I can figure out what the slope of my tangent line is at a particular point, say at the point x equals 2. By substituting in 2 into my derivative function. And as a result, I can find the equation of this line by using the point slope form. Y minus 8 equals 12 times x minus 2. And so what's nice is that once I have a derivative function, it's very, very easy for me to just by substitution into my original function and my derivative function to come up with equations of tangent lines. And similarly, I could also come up with equations of normal lines just by taking the negative reciprocal of that quantity. However, this notation that we've been using, this f of x plus h minus f of x over h, is not always the easiest to use depending on our function. There are some situations where an alternate formula would be more helpful. And this alternate formula for the derivative is the limit as x approaches a of f of x minus f of a over x minus a. Now, I can still think of this as kind of as x approaches a. This is going to give me the derivative at a. So I'm going to get the instantaneous rate of change at a point. But once I've found it in terms of an independent variable a, I can just change my independent variable back to x and actually get a derivative formula. And the situations where this is more helpful as an alternate formula for the derivative are situations like this, where I have y equals radical x. So if y equals radical x, and I want to find the change in my function with respect to time at a particular point a, I want want to take a look at this using my alternate formula. The limit as x approaches a. And this ends up being radical x minus radical a over x minus a. And remember, as always, our idea is 1, because I can't substitute, I need to try another line of attack, and this other line of attack is always to try and use some type of algebra to eliminate a common factor in the numerator and denominator. And in order to facilitate that, I'm going to take this root x minus root a and multiply my numerator and denominator by the conjugate, root x plus root a. And this is usually my mode of attack whenever I'm dealing with radicals that I can't eliminate, is to try and multiply by the conjugate. Remember, the purpose of multiplying by the conjugate is to get a difference of squares issue here. And this ends up being square root of x squared minus the square root of a squared over x minus a is one factor in the denominator, and radical x minus radical a is my other. And I'm still looking for the limit as x approaches a to find this derivative function. And of course, as was our ideal situation, I have a common factor in the numerator and denominator. So I'm left with the limit as x approaches a of 1 over radical x plus radical a. And in this situation, I can actually substitute a for x. So I end up with 1 over radical a plus radical a, or 1 over 2 radical a. And so if this is my derivative at point A, that means that my derivative at a variable x would be 1 over 2 radical x. So I can still get a derivative function even in a situation where I ordinarily was just solving for a particular value of a. And so this is a situation where the alternate form of the derivative is going to be more beneficial in calculating the derivative function. So the last thing I want to talk about today is a third method of calculating the derivative, and it's called the symmetric difference. The idea behind the symmetric difference is sometimes it's not easy to just substitute x in. And so what we'll do to find the derivative at a particular independent variable x would be to find the limit as h approaches 0. But take this symmetrically. Take x minus or x plus h and subtract x minus h. Of course, if I do that, my width between x plus h and x minus h is really 2h. And so I need to make sure that I put this in here. It's not just h, it's 2h, because I'm h units away on the positive side and h units away on the negative side. Because what I really have here is I really have x plus h minus x minus h. So that's where that 2h is coming from. And the benefit of using this symmetric difference formula is because this is how our calculators calculate a numeric derivative. By taking this for some very small value of h, like 0.00001, and this is something that's called the tolerance. And you can actually set this in your calculator to set how accurate your calculation is going to be. Just realize that the more accurate you want your numerical instantaneous rate of change to be, the more time it's going to take. But this is a still third version of the derivative, the symmetric difference. And this helps, especially in a situation where the derivative wouldn't ordinarily exist because it's difficult to deal with x by itself in the original function. So what we're going to talk about tomorrow is we're going to be talking about more applications of the derivative, and we'll also do some more examples of how to calculate the derivative. And we'll also deal with derivatives that exist only at one side, because we learned from before that sometimes a function may not be continuous. I may only be able to look at it from one side, and so I may have what we call a one-sided derivative if I'm dealing with a boundary point to my interval. So that's all for tomorrow's lesson. Thank you very much for watching. This is Mr. Potter. Have a great day.